So thanks a lot for the invitation, Dmitry. As you see, the topic of today will be probabilistic graphical models, and I will focus on factor graphs, which is our main research fields. I'm from the signal processing laboratory of ETH Zurich, and my supervisor is Professor Hans-Andrea Löniger, and his main research focus is factor graphs. So here to give you a brief overview of what I'm going to talk about. So first of all, I'm not familiar with the audience, so I will just quickly recap what graphical probabilistic models are. Then I will delve deeper into this specific form of graphical models, namely factor graphs. I will show you one input estimation algorithm, which we developed in our lab, and we're going to present in a biosignals conference. Then another quite hot topic is local statistical models. And finally, if we have the time, we can even go into learning in Bayesian networks. But I prefer to do this talk in a bit more interactive way. So if you have questions, just interrupt me. I'll be happy to answer if I can. Otherwise, I can write down the question and answer you later on. Thanks. So don't fall asleep. I'll try to make it interesting. So just to go really back, so what is scientific modeling? Well, we have real-world phenomena. I just chose, being from the electrical engineering department, I just chose the Maxwell's equations. And so we put in a set of mathematical equations a real phenomena. So here we have the Divergence Law, which describes that electric currents, they generate an electric field, or the divergence of the magnetic field is zero. That means we don't have any magnetic charges. And so with these mathematical models, we can just describe real phenomena, we can predict behavior. And furthermore, connected to these mathematical equations, we can have visual graphical representations. So in this case, I just chose an image of I think it's quite hard to see, but it's just magnetic field lines which are closed of a dipole. And I don't know the Russian sentence for it, but like in English you say, a picture is worth 1,000 words. I suppose there's a similar adage in Russian.
Yes.
Exactly. So that's why I chose the topic of this slide. Engineers love graphical models. So not only in science, but especially in engineering. My background is from control engineering. That's why I chose this feedback control loop. So this is one graphical model which says, okay, my output should follow my reference R. This means that if my output y is equal to my reference r, I don't have any error inputs, and my y will just stay like this. On the other hand, if my output is not following my reference, I have a non-zero error signal which goes to the controller, which is then fed into the plant, and so we can steer our system. For instance, if we have the heating system, we want a specific temperature, and we make it to follow. In order to design these controllers, engineers just use graphical models. I heard that here's the computer science department, so I took just another example, the Petri nets, which are used to model like concurrent executions and distributed problem solving. So here you have this bipartite graph with the places and the tokens inside and the transitions, which you can model then like parallel problem solving. But in our case, there's one more thing, that there's uncertainty. So where does this uncertainty come from? On the one hand, we can have that our system we want to model can only be partially observed. So if we have some chemical process, we cannot measure all the temperatures in all the vessels. We might have noise measurements, which is quite common if you have biosignal processing. So the measurements, if you have an ECG signal, they're quite noisy. And we might have incomplete knowledge of the system. We don't know completely how things interact in very complex systems. And on the other hand, we might have systems which are by nature, so intrinsically stochastic. This happens mostly, for instance, when you model chemical reactions. So the chemical reaction occurs when two molecules collide, and there's a lot of probabilistic modeling behind that. So in this case, to handle this incomplete knowledge, these mistakes in modeling, and the noise, we use probabilistic models. And how do we capture probabilities? With the probabilistic model, we have a set of random variables, x1 till xn, on some probability space. That means we have a sigma algebra on these random variables and a probability measure. And for these ones, we can define a joint cumulative distribution. This is this case. And then if we took the partial derivative with respect to all random variables, we get the joint density. And for all joint densities, you can factorize them with the chain rule. So I chose the notation, so xn conditional on 1 till n minus 1, and then n minus 1 conditional on all the previous. And another quite important concept we're going to use for the graphical models will be the concept of conditional independence. So if we have two random variables, x1 and x3, and so this is not a time index. It might refer to a time index in a stochastic process, but this is just some index, some random variables. So two random variables are conditionally independent given x2 if their joint density of x1 and x3 factors in this way. And that's what we're going to need for the graphical models. So we're talking now about structured statistical models, so a statistical model which has some intrinsic structure. So usually when we have a model, not all random variables and all quantities depend directly on each other, but we have conditional independencies. So for instance, if we took the hidden Markov model, which is the joint described by the joint density from my hidden variables x0 to xn, and also my observations y1 to yn. This factorized in the following way. We have a prior on the initial state, and then we have this Markov property that the current state depends on the previous state, and my observation depends on my current state. And so what we're going to use in graphical models is the lack of edges. The conditional independencies will help us to generate graphical models where we see how the random variables interact with one another. So I'll talk about three of the, I think, most used graphical models. What are graphical models? First of all, they're graph-based representations of these joint densities. The joint densities, they describe like the behavior of how all random variables interact. And so I'll talk about Bayesian networks, Markov random fields, and then I will focus on vector graphs. Bayesian networks are a class of probabilistic models. They are described by directed acyclic graphs, so we don't have loops. And their main focus is they describe these conditional dependencies between random variables. Markov random fields are non-directed, so the edges don't have arrows, and they're mostly used for modeling spatial dependencies. I know that Vetrov's group is working a lot with computer vision, so if you have a pixel and the neighboring pixels depend on that, there is no purpose on saying there's a causal dependency on the color, but still the colors of one pixel and the surroundings have to be somehow related, because objects don't change with one pixel to the other. And finally, I'll show our favorite graphical models, the vector graphs. And they look slightly different, but they do the same stuff, and they show explicitly the factorization of the joint density. So let's start first of all with Bayesian networks. As I said, one network is representing the joint density. And we can see here, this is an example of a Bayesian network where we see that this is an acyclic graph. There is no connections, and we have the arrows indicating conditional dependencies. So the nodes are obviously the random variables, and the edges show the conditional dependence. So as a quick exercise for the students, just take a pen and paper and write down the joint density of that one. I know it's quite easy, but just to get everyone on track.
And I think you should give a hint that joint density can be written by, well, chain rule, and by the rule that this is a product, or probabilities of each node given all of its parents.
Yes.
Right?
Okay. Right. This is good point. It was a bit too much in the dark then. So yes. In this case, this arrow shows the conditional dependence. So just to give you one hint, you have this node which represents the random variable x, and it is conditional dependent on these two parents, which is u and w. So one of the factors in the joint density is p of x given u and w. On the other hand, we have w and u, which don't have parents. So there's just a prior on them. So this is a single factor, is p of w and p of u. So now I've almost given you the solution. I see most of you have done with writing. So we can uncover the solution. What everyone was expecting, we have the Bayesian network represents the joint density, so the probability of all random variables involved. We have u, w, x, y, z. And so we have the two priors on u and w. X is conditionally dependent on u and w. And here we have y is dependent only on x, but conditionally independent of all the others. And z is only dependent on x. So there's two ways actually to come to this, I hope I'm not covering that, to come to this joint density. So either you think about conditional dependencies. That means you start off and say x depends on w and u. Or you can think about, as I showed before, you start off with the joint density, with the whole factorization. So you can say z dependent on all the other random variables. But then you have conditioned on x, and you see if you fix x, z is not dependent on the other random variables anymore. So this is, from a fully connected graph, we get down to this Bayesian network. So the lack of edges is what we care about. Because the lack of edge means there's a structure behind this graphical model. Okay, so now just to see similar representation of the same joint density with a Markov random fields. So not much changed. If we look, we just had here one edge for demoralization to make a Bayesian network into a Markov random field. And here we have undirected edges. They represent now dependencies. They don't represent conditional dependencies, so we forget about causality, but we have a dependence here, structure. And again, the variables are the nodes. And here we have the factorization of the following form, so the same as we said before, but usually as you use them, this Markov random fields is you look at clicks of like connected nodes, and to have a unique factorization you use like maximum clicks. So this is one of the biggest click involving w, x, and u, which is shown by this factor. Then we have x and y, which is this psi factor, and then we have x and z. So now we can get to vector graphs. Can I just see like how many of you are familiar with vector graphs or have ever heard of them? Okay, quite a lot. I'm happy that we're making good advertisement of those. So, what is a vector graph? Well, vector graph, they represent a factorization of a probability density function, the same which was true for Bayesian networks and also of Markov random fields. But we have a bit different way of representing it. Namely now, the edges represent random variables and the boxes represent vectors. So if we take the same joint density as for the Bayesian network at the Markov random field, we have this vector graph now. So before in the Markov random field in the Bayesian network, we had that the nodes represented the random variables, but here we write the random variables on the edges. So for some of you, which this looks new, this is like this Forney style vector graph notation. The original vector graphs, they had here circles, but as far as I'm concerned, these are currently the most used notation, or at least what we are using. So,
but are these notations equivalent?
Yes, yes, exactly. Exactly. So,
wait.
Yeah.
And what if variable w is involved, say, in three factors?
Yes, in this case we need the equality sign. So it's a good question. So let's look maybe at this vector graph. So the rules are, as we stated, that the boxes represent vectors. So we have this joint density, which can be written due to conditional independencies as this density. And each edge stands for one unique random variable. So if you say, okay, one variable appears in more than two vectors, you need to do something. You need to introduce this so-called equality node. This equality node states that here's x prime and x2 prime. And so we said this box is a vector, a function. But this equality node is still a function. So how can you describe this as a function? You write f of equal of x, x prime, x2 prime. And you could write this, so assume that our random variables are discrete. So we have x minus x prime times delta, discrete, x minus x2 prime. So now if you consider the configuration space, so like all values all random variables and also this auxiliary, this helper random variables x prime and x2 prime can take on. The configuration is only valid when x prime is equal to x and x2 prime also. And this, how you make x appears in 1, 2, 3 vectors, and this is how you do this with the equality node. So there's also a plus node, which would be such a thing, and if you had, I don't know, x, y, and z. Vector graphs are not oriented graphs, so they don't have edges, but sometimes you just write it to show some causal relationship. So maybe it's called it to be correctly in the alphabetical order. This is z. So when we have some hard constraints on the variables z equals x plus y, you can write this vector f plus. It depends on all the edges it's connected to. So x, y, z is delta of z minus x plus y.
So thus we establish some deterministic relations in
Yes,
our probabilistic
perfect.
model.
Exactly, yes. Should I pull it down or is it electric? I think I'll need it another time. Perfect. Thanks a lot. So yeah, anytime you have questions, interrupt me. I hope I can answer. So as we said, as we established before, so there's a unique node for every factor in our distribution. There's a unique edge. An edge connects two factors, or a half edge, which is just connected to one box for every random variable. That means that we need this equality sign to replicate random variables which appear in more than two factors. And this rule, this uniqueness, means that if an edge is connected to a box, the box is a function of that edge. So here I drew a small vector graph. Can you write down how the density factorizes? And then you can say basically which is the conditional independence. So which two random variables are conditionally independent.
I will start asking questions for my students.
Is it not common? Like this is. Because I feel I'm hitting some laughter. Is it not common to make questions in presentations here? Okay. So anyone wants to give a try? It just helps me to make sure if you understood what I'm saying or see it or not.
Well, there will be three factors, I think.
Yes, perfect.
One will be ex of x.
Yes, very good.
Times something dy1 conditioned on x.
Perfect.
y2 conditioned on x.
Yes.
And therefore y1 and y2 are going to be conditionally independent.
Perfect, yes.
Thank you, Professor Sabadevsky.
I
You're
apologize.
welcome, Professor Wadehn.
I apologize if it was too easy. It was more meant for the students, not for professors. I have no doubt that professors know this. So yes, so this is exactly the case. We have this factorization of the joint, which is y1 given x and y2 given x. So it could be some like, we have x, which is some random variable, a chance variable, and y1 and y2 might be two observations with different noise. And we can do then inference on this vector graph through message passing and estimate the posterior, the likelihood, or whatever we want to do.
Why do you drop the dependence on y1 in the arguments of the factor?
Oh, well, it's kind of a notation. So f of y1 given x, it's a function of y1. So you have a random variable, y1, which has a distribution. And now you condition on x, and you have a new probability space. So your possible space is now not y, but y given x.
Okay.
But your
this
density...
conditional distribution depends on x small. Right?
Yes, yes.
On a particular value.
Yes.
So to be formally correct, you need somehow to indicate it.
Yeah, I had it before, it's true. But yeah, you're right. So, but there's a lot of abuse of notation. I have to be...
Yeah.
But you're completely right. So if you want it... Yeah, because it's given a specific x, because this x is small here.
Yeah.
So yes, good point. You got me there. So to give a summary of this 3 or 3.5 different graphical models. So we have this Forney vector graph. Forney was a guy, I think he either wrote the seminal paper or invented the Viterbi algorithm. So he's a coding guy. He used these graphs in coding. And so we have this Forney vector graph where the variables are on the edges and the boxes represent the vectors. I think when the vector graphs were originally published, they were using this intermediate notation with this nodes in between, but the description is actually equivalent, and some way, my professor always says this is the right way. I don't believe there's a right way, but somehow we prefer this. Just to be curious, if you're using vector graphs, are you using this or this notation?
The right one.
Right, so you see it's completely equivalent, so just pick the one you prefer. I think it's maybe nice when you write messages on the edges, and it's quite clear that you have the message on this edge is from this variable, and the boxes exchange messages. But I think, yes, it's just up to flavor and taste. So the Bayesian networks, as we remembered, we have edges, conditional dependencies, and the Markov random field, which is this one. It's mostly used in statistical physics or computer vision. Yeah, I had quite a lot of exercises for you. I apologize because I heard that I should give a lecture style and not like a conference presentation. So if you're bored of that, I can also click and give the solution right away. But the exercise would be, if you don't need to draw it, but just maybe try to visualize it in your head. So we have a hidden Markov model. So we have a joint density. It's a model which is structured. So we have some conditional dependencies, namely they're quite strongly conditional dependencies. We have a lot of edges which will disappear. Namely, we have that the joint density can be factored as a prior on the first state. And then we have P of x depends on this previous state, so the Markov property, and the observation y depends also on the previous state. And we can, I know there's some ambiguity sometimes if like y is an observation of xk minus 1 or yk is an observation of x. Yeah, forgive me for that, but it's just, yeah, there's different notations that we can choose. And so we can factor this again in more detail. So this is the transition probability, also called transition kernel. And this is the ejection probability. It means like to eject, what we observe are states. So how would this joint density be written as a vector graph? Just try to picture it in your head quickly before I give the solution. So you ready for a surprise? Yes. Okay, so we have on the one hand the vector graph above, shows that we have a prior on x0, this is this box. Then we have transition, it's the whole factor here, it depends on x0, so which is xk minus 1, xk, and yk. And so we have here, this is the whole factor graph. It goes up to, in this case, n, and beware that here will be then xn. There's no factor on the right-hand side. Otherwise, you would make a contradiction. And here you see one of the nice properties of factor graphs. They're kind of like, I wanted to buy from my professor Matryoshka because it reminded me of factor graphs, because you have boxes inside of boxes. So you can open a box, and there's a factor graph inside of that. So you can open and close box, which is quite the main principle in message passing later on. So you have this one, this box here, and you see that again we make use of this equality constraint, which introduces like some hard constraints, deterministic constraints on the random variables. So this box here is this one, and this box is this one. So we open up Matryoshka principle and see that here we have x0, x0 prime, x0 2 prime, and this one is the ejection probability, so this factor here, and this one is the transition through in our hidden Markov model. So it's called hidden because what we do observe is, yeah, it's a bit cut right now. It was a bit bigger before, right? Or was it always not completely on the screen, the image? Doesn't matter. I hope you forgive me for that. So here I would have written y1, y2, and so forth. So here it's called a hidden Markov model because you have a hidden layer, hidden variables, which you do not observe, and here the observed layer of y's. So exactly. To give you some applications of Kalman, of factor graphs. So I'm coming mostly right now from the area of statistical signal processing. That means that some time ago, basically, we went away from signal processing in the frequency domain. So usually what you do is you have a signal, you take the Fourier transform and look at the frequency domain. But mainly in biosignal processing, what happens, even if you do the short-time Fourier transform, you lose temporal information. And when we look, for instance, at what we do, like at heartbeats and different electrical signals coming from the atrium or ventricle, temporal information is really essential, and that's why we use like state space model signal processing. Other like very high performance algorithm would be like wavelet methods. They also use this temporal resolution. So actually, factor graphs, some algorithm of factor graphs are actually equivalent to Kalman filtering and Kalman smoothing on state space methods and models. I'm not at all in coding, but half of our group actually is from coding because my professor originated from coding. He was like a PhD of Messi, this guy did this kind of turbo codes. So we can see later on, I will draw it on the whiteboard, a factor graph of a Hamming code or of an LVPC code. And so these factor graphs can be used for decoding such low density parity check codes. And yeah, factor graphs, as you might know, they're used in a variety of applications. I even heard 2 of your PhD students try to predict football games with factor graphs, so it's awesome. Yes, so I saw some examples in genome analysis, so you can, I think whatever application you might want to use, you can employ graphical models, and if you want, factor graphs. So I just showed you just a Kalman filter because I read this high school of economics, and I suppose that for economics students, a Kalman filter can be quite useful. It usually originated from control theory, but you can imagine this is a financial time series. So the red one, which is observed with jumps, and then we use a Kalman filter to estimate the mean, and we get also the covariance of your states. So you can use this to predict states, and yeah. Apparently some people try this to like track stock prices and make money of it. So now let's get to the main algorithm actually with factor graphs. It's called either belief propagation or message passing. You call it message passing, but belief propagation originated originally on Bayesian networks. It was the term was coined by Judea Pearl, which was quite a guru on Bayesian networks. So this message passing, or this called sum product message passing algorithm, is used to do inference. That means to learn parameters in factor graphs. And what we can do with this sum product message passing is we can recursively compute marginal distributions. And when we have given random variables, and it's called message passing because messages are exchanged between the factors of the factor graph. So I just chose a stupid example again from economics due to the name of your university. Here this guy says, I've got a stock that could really excel, that means perform very well. And this says really excel, and then they hear the wrong message, sell. So if a stock would be good, you wouldn't sell it. And here's the same sell, they just go crazy, shouting sell. And his guy says, this is madness, I'm gonna go away, goodbye, bye, and everyone says we should buy it. So it's just a stupid example.
But it illustrates well the work of message passing algorithm.
Exactly. So this is, I think it's called Chinese Whisper, this game which children play. And
we call it in Russia spoiled phone.
Spoiled phone, yeah, exactly. So, so you have it. And less funny, more serious, belief propagation on factor graphs. So as I said, this message passing, especially the sum product message passing, can be used to compute marginals by summing out all the other random variables in the factor graph. So we have this joint density we have this model with 7 random variables, x1 up to x7. I just used the shorthand notation because there's no space on the slide. So 1 double dot 7 is MATLAB notation, so all the random variables. And we further assume there's some structure in the model, and we assume that it factorizes the following way, like this. We have 7 factors, we have here x1 is alone, x2 is alone, but here there's g3 which depends on x1, x2, x3, and so forth. And the usual way how to compute the marginal would be how? We sum over all random variables except x3. So here I missed x3. And what do we do? Well, we have to do here, assuming we're in decoding or something, that we have binary alphabet for each random variable. That means we have 2 sums times 2 sums times 2. And that means that if we have the sum here, the marginal would cost exponential in the number of the random variables. So 7 is not a big deal, but when we have like this low density parity check codes or turbo codes or polar codes, the code words are huge, like, I don't know, 2,000 or more bits. And so this exponential brute force computation would become like prohibitively expensive. And that, but we can use the structure actually of our graph, of our distribution in the following way. So we have x3 of x3, f3 of x3, which is the marginal, and it's still, we get it by summing. I hope you can see it. We sum over x1 and x2, over x4, x5, and x6, x7. But now, since, for instance, G4 does not depend on x1 and x2, we can take out the factor and distribute it. And now we see the nature of this recursive computation. So for this graphical model I wrote before, for this G1, G2 times, for this factorization of the joint density, we can draw the following factor graph. It's this one. So we have here x1 on this edge and so forth. And now this sum here, by using the structure we redistributed the sum, and this sum will be called message u x5. This means this is the message on this edge. That's why I said like it's nice to have edges, the message off this edge. And so how do we get this message? Well, we sum over all internal variables and we get this one. So why is it called belief propagation originally? Well, these nodes here, they communicate what they know about x5. So we have some knowledge about x5 in here. And this is what they communicate. They communicate their beliefs. That's why it's called belief propagation. The beliefs, they work through the network. And then we have the message on x5, but we wanted originally to have x3. So we have to propagate our beliefs further. Here we sum over the internal variables x4, x5. So we close this box, and we get message mu3 backwards. And here we get message mu3 forward by closing this box. Yes?
What if you have equality box? Do you have to like have a message mu x5 prime or something?
Yes, exactly. So you introduce just auxiliary variables, but the message passing is the same.
So you have, if you have an equality box, you have to say this h is x5, this is x5 prime, and this is x5 2 primes, and you cannot like swap them afterwards.
Yes, I can. Let's see if I can draw. I'm not completely sure I got your question, but I'll try. So you said you have an equality box, and let's assume we have, I don't know, 2 messages coming in. So this is x, this is x prime, so this is mu x prime, this is mu x2 prime. So the message, so beware that factor graphs are not, as I said before, they're not directed, but I just write edges, arrows like this to have a unique notation for like forward or what is backward messages. But I could also swap the arrows and just have to turn it around. So there's no causal relationship. You can use it to describe it, but it's no causal relationship. So the message mu x forward is you get it by some product message passing. That means, let's assume for the ease of computation, they're discrete random variables, so we sum over them, we don't integrate. So we have the sum over all x in its probability, in this space that it can take. Then we have the sum over x2 of what? Well, of the incoming messages, mu of x prime, mu of x2 prime, x2, times my factor f equal x prime, x2 prime. And so well, this is just a delta, right? So what happens is that all the factors will drop and you just have mu x prime of x, because the delta ensured this one, times mu x forward of x. Yeah, but very good questions, I like this. I apologize. Yeah, not planned slapstick humor, I'm sorry. So, okay. So this is quite an important algorithm. This is the sum product message passing. What you can also do is the max product message passing. So instead of summing, you have here, you maximize over the random variables, which is also kind of a marginalization. And yeah, unfortunately it's quite cut. So what you see is that the marginal is the product of the forward message mu x3 times mu backward x3. So yes, to give a summary of the sum product message passing algorithm is that we have here the forward message of some node xk is obtained by summing over all random variables but the variable xk of the factor and times all the incoming messages. So I just plugged in the case of the equality node. And I know you don't like exercises, so I'll give you again the solution. But we have this general form, it's quite easy, just have to plug in the indices. And so what is message mu x1 in this vector graph? Well, you just have to sum over g1 up to 4. So this will be a function of x1, because you sum over x2, x3, and x4 of message mu2, mu3, and mu4. And beware.
And pay attention that instead of having exponential complexity, we now have linear complexity.
Yes, that's very important, exactly. You could see that here, actually, in this one. So depending on how big my factors are, the complexity It increases, but yes, in the ideal case, you can. So if you have something which completely factorizes, you would have linear complexity, and before you had exponential. So it's quite a big gain, as you pointed out. Yes. So you can see here it's like 2 and 2 and 2 summations. So you have just like this sum and this sum, but not like
The joint sum.
yeah, exactly. So yeah, this is actually the main point. If you're familiar with control system, there's like this algorithms called dynamic programming, which is kind of recursive plus memory. So you do recursions, but you have memory, and the memory is stored in my messages. Yes. So what do you do? Do you do breaks or just all through, just as you want?
Usually we do not.
Okay,
make
perfect.
Breaks, but we need to finish at what?
Well, in principle, we have 90 minutes. And we started at 4,
So half past 5.
Yes.
Perfect. Yeah, just switching. I just don't want to overstrain the capacity because I think 90 minutes, the brain cannot register 90 minutes, but you can watch it online, I hope. Okay, so as I said, like this trend is going to like signal processing on state space methods. So just to recap, what is a state space model? It's this model here. So you have xk, it depends on ak minus 1 with a matrix which transforms the states. Then we have an input uk, and you have yk, which is the projection of my states, and plus some noise. So here you have exactly the structure that Dmitry was pointing to, that you have some mixture between some probabilistic input, with this one could be like white noise and the usual Kalman filter, and you have some deterministic constraint between the states, which is this one. Obviously this can also be eased by having time-dependent transition matrices, and there can also be some randomness inside, so you wouldn't have a product here, but you could have some probability density inside. But with the normal simple factor graph, we have this form. So this state space model with white Gaussian noise, which I didn't write in here, should be a new factor, can be written down, the state space model with this factor graph. Now, having established a factor graph of the state space model, we can find out, basically, we can do inference on the factor graph. We can estimate inputs by computing the messages upwards. We can compute the states, which would result to the Kalman filter if we go forward, or if we go backward, it would be a Kalman smoother. And note that we had already discussed the equality constraint and the plus constraint, but this is a factor, so this can also be written as a delta. I will not write down, but this would be just like a delta of xk prime, so to say, minus xk minus 1 times a. So this factor here is again as a factor graph, all boxes represent factors, this is a delta. So this one minus a times this one, the delta of that. So who's familiar with the Kalman filter? Okay, so yeah, so it's more about from control. So I know that in computer science might not be the most common algorithm, but it's the hot shot algorithm in control. So what is done is we have this state space model, and this is reminiscent, actually it forms like a Markov chain. You see that xk only depends on xk minus 1. And we have this ejection probability, in this case yk depends on xk, not xk minus 1 as before, but as I said, there's always some arguments how you define it with the indices. So we have, again, a hidden Markov model. The hidden layer is my state x, my observation is y. So the Kalman filter is a recursive algorithm how to estimate my states. So you compute actually posterior on your states, but since we are in a Gaussian setting, which means that my input u is either deterministic or is Gauss distributed, and my noise is white noise, so uncorrelated white Gaussian noise. What we have is we want a posterior distribution on the state, but since it's Gaussian, the whole distribution is described by the mean and the variance. And so we start off with some prior knowledge of our state, some distribution on x0 or on any state, and then we can recursively update the mean. So we use basically to get this one, we use the model. So if we have xk minus 1, we can just compute xk. So the mean propagates deterministically, and the variance does not because of this factor here. But then we have also an update for the covariance matrix. But now we get an observation, namely at time point k, and we use the observation with its noise statistics to update, to make a correction on the mean and also correction on the covariance matrix, to make a prediction, an update or correction step. And finally, what you get is just to see a state estimate of every step. And this is what I showed before with this financial time series. You estimate some internal state and you just plot it. And so this Kalman filter can quite easily be described as just some product message passing in a vector graph. So there's quite a lot of common, really heavy algorithms which can be easily described as instances, as examples of some product message passing. So what we assumed is we have Gaussian messages because our input was Gaussian, our noise was Gaussian. So when we propagate our messages in our vector graph, they stay Gaussian. So this is the property of Gaussian random variables, that they are closed under addition and multiplication with constant factors. So they remain in the same family of exponential distributions, namely of the normal distribution. And Kalman filtering is we want to estimate those states given my observations. In this case, I chose just for a space an autonomous model with no input. But if you had an input, you just had a plus node here and as before. And so traditional Kalman filtering is forward message passing. What does it mean? So the posterior of xk, given all my measurements up to point k, is exactly this message mu xk forward. So what we do is we have here a deterministic factor. When we observe it, we send this up. So if we have measurement noise, we would send up a Gaussian message with the mean y1 and the noise variance, which is here. This factor comes in. And then we compute with these update rules, as I showed you before, with the box. Just get back 1 second to with this one. How you update messages. You can compute ux1, and then you go further and you join these two messages over the equality node, and so forth, and you can get all the messages. In this case, you don't need to work with distributions because in Gaussian message passing, you only need to propagate the mean and the variance. This is enough. And there's update rules for these vectors, which make it very easy just to write down the Kalman filter like this. And yes, finally, you take the mode, the mean or the median, it doesn't matter, it's all the same for the Gauss distribution to have the mean estimate. So yeah, Kalman filtering is forward message passing. If you took also the backward messages, it means the information you get about xk giving the future, because the future depends on xk. So also knowing in an offline processing way the future is, gives you more information. You can get better estimates of a lower covariance if you don't have infinite number of samples. Exactly. So forward message passing is Kalman filtering, and forward backward message passing is Kalman smoothing. It's called smoothing, has reasons to take the future into account. Yeah, just here just some small examples from biosignal processing. I try to keep the medical terminology very low, so my artistic skills is you have a human and it's lying on the bed, and when the heart beats, your body wiggles. So there's force sensors, usually more than 2, but in this case I just draw 2. And you have this ballistocardiogram. Ballisto means this force, and cardiogram just recording of the heart. And so you have this blue signal, and the red is just like the heartbeats. And basically the goal is, given this ballistic cardiogram, actually multi-channel. And the better is like to have many channels, because the state space models are really good to work with multi-channel data. And so our goal is to get from this signal, we just extract the heartbeats. So the signal is disturbed by noise because the sensors are not perfect. And also there is like movement artifacts. So when you move a hand, you destroy the signal basically, because any body movement is much stronger than what the heart can do. And there's also respiration, which also is overlying on the signal. So our goal is to find the heart rate variability. The heart rate variability is just the distance between the different heartbeats, and if you have a good heart rate variability, it means your heart can react to efforts. It means you're kind of healthy. If you have quite a uniform heart rate, that's even bad.
Really?
Yes, it's quite surprising, but like older people have a rather uniform heart. It means it cannot adapt.
And what about heart arrhythmia, for example?
Well, that's then too bad. Yeah, I mean, there's two extremes, obviously. If like arrhythmia, yes, but to some degree, some non-normal beats are not very harmful.
Okay.
But yes, yeah, obviously, you can go to the extreme and like when it's not good anymore. And when we estimate the input, we can also estimate the strength of the heartbeat, which is kind of an indication of the cardiac output, so how much blood is getting pumped around your body. So what we chose is statistical approach, and we do a likelihood filtering to find the positions of the heartbeats. And so we have this ballistocardiogram signal, the blue oscillation you saw, and we model this with a linear state space model. And to find the input, we do a maximum likelihood estimation of the heartbeat position. So what we do is, yes, we have this state space model. And the state space model is being fed with an input. So the input is, which shows a non-uniformly distributed dirac. So we have here the variation in the heartbeat times, and here we have the amplitude. And this blue signal, what you saw, is then my observation here. The C decides on how many channels you have. And so my BCG, my ballistocardiogram, is just the impulse response of a linear combination of these inputs, which gets transformed in the state space model. So what you have finally is an exponentially decaying oscillations. Because the state space model is basically, you can take an ordinary differential equation of nth order. When you write this down in state space form, you transform from the nth order to first order, and that means you can describe oscillations by that. So basically, when we have an nth order differential equation, let's make it quite simple. Let's take a simple oscillation. We have, I don't know, a pendulum. We have a pendulum here, and this is my oscillation. And so you have some y2 is minus some constant alpha y, and it goes against also my, so this is my acceleration is the displacement here, and also it goes against, you have a damping. So this is in second order ordinary differential equation, and now we can transform it easily by introducing a state, a vector x, and we have here y and y dot. And so basically, if I write down our x dot, which is the same as y dot and y double dot, and so y dot was, we call this x1 and x2, so y dot is x2, and y double dot, as you can see here, minus alpha y is x1, and here you have minus beta y dot is minus x2, minus beta x2, so you have x dot is equal to 0, 1, minus alpha minus beta, x1 and x2. So you have now x dot is some A matrix times x. So this is first order. So you can transform any ordinary differential equation of nth order with constant coefficients into a first order differential equation. So now that we see that we can take any nth order differential equation, transform it into first order, so it's equivalent to a state space model. Why I'm going up? So I'm going down. And again, state space model can be described as a vector graph, and with this one we can now easily describe our inference problem. So what we want to compute is basically the likelihood of an input. What we do is an hypothesis test. So here we're a bit basing ourselves on knowledge of the physiology of the heart, that some heartbeats need to have some distance between each other and so forth. So we have a hypothesis test. We have k hypothesis. So hypothesis HK says that if you consider a window, there's supposed to be only one heartbeat on this window. So if we take a look on this picture, we have this potential window where the heartbeat could be, and we want to find the one position where it is. In this case, we assume quite like healthy heartbeats, but it's just to get an average heart rate in this bed, so we don't want to have like high precision medical devices. So if I have a window of m samples, we want to find the position where the heartbeat is. So out of the m, we want to choose one position, but we leave the amplitude, the strength of the heartbeat open. And so what do? We need to compute the likelihood of the input. What we take is the whole joint density conditioned on the input and with the observations plugged in. And so this is the likelihood for the hypothesis HK. So all inputs are 0 except the kth inputs. And how do we compute this marginal likelihood function? Well, we have to sum out or integrate out, because they're continuous variables, over all random variables x, over all hidden states. And what we do is we need to compute basically the forward message, the backward message, and then we get the marginal. So this is almost the likelihood that we want. So with this one we get basically forward backward message passing, and we're here. So the joints. And now we just need to go up with the update rules, and we get the likelihood function, this one. Yes, then we have we have this open amplitude, the UK, and we just integrate it out, assuming that the impulse is positive due to the heartbeat. So we integrate from 0 to infinity, and we get just p of y given the hypothesis. And then we have m hypothesis for each position, and we just take the maximum over the hypothesis to find the position which was the most likely. But with the message, we also have the posterior distribution of the inputs, and that mean we will take as the magnitude of the input. So we found the position and the magnitude. Yeah, so this is just, how do we choose the hypothesis? Well, we start with a big window, we find the heartbeats, and then you know that the heart rate cannot vary too much, so we have this jumping windows, which depends on the previous heartbeats. 2 or 3 depends for the stability. And then on this one you have the center, and somewhere around this the real heartbeat should be, and you find it. Yes?
So if you move on this device, will you like break the
model? Yes. Yes, exactly. So you need to re-estimate the model, basically. So when there's a big, if you're lying on your back, there's one state space model, one A, B, C matrix describing this dynamical system. But when you just change on your sides, the model changes, obviously. So when there's big movements, you have to re-estimate the system matrices. Yeah, very good question. This is, yeah. Yeah, so what you get is like a pattern, like the blue ones are the ECG, which is a reference, and then you get like the positions of the estimated beats. The good thing is with the state space model, it is quite high order, it's like 14th order, but that means it contains a delay between the electrical activation, which is the ECG, and the mechanical activation, so you even find when the electrical activation was. And when there's some movements, it just misses it. And you can see actually from the likelihoods that the likelihood values drop when the model is not able to explain the observations, when there's artifacts. So we have some automatic artifact labeling too. That's not important, it's just some performance metrics. If you have the real heart rate, the blue one, and if you estimate it, kind of follows it. And yeah, we tried with 12 subjects and 10 minutes recordings, which is not very long, but enough to get a proof of concept. So now, completely different topic. So, yes, I think we most likely will stay with this one. We'll get deeper into this one. If we have time, we can also give a look at that, but this is not about factor graphs, so we can easily drop it. So, as we said, like message passing, this super important algorithm on factor graphs can be used to compute marginal distributions, so distributions which depend only on one random variable, and they can then be used for maximum likelihood estimation by marginalizing out all internal states, or for maximum a posteriori estimation if we get, for instance, the messages of the input as before. And until now we have kind of circumvented the problem of having that we use basically windows, a windowed approach, that because we fitted the model only to a short window basically. And now what we do is we locally fit the model. So it's quite a paradigm change. Instead of fitting the model to the whole signal, which we have, we just fit it locally. So what does this mean? So we take a model. In this case, we use a state space model, which is quite versatile. It can describe a variety of signals. There's oscillations, for instance, or also a straight line. And we fit this model to the data. So in this case, I need a whiteboard. So our main working horse in this example is this autonomous model. This one. Okay, now we see better. So in this case, I just need my laptop, 1 second. Just to see it. Perfect, exactly. So we have, this is my autonomous model without an input, and we will locally fit the data to our model. It means the state space model is quite versatile. So for instance, if we took an A matrix to be 1, 1, 0, 1, and a C matrix to be 1, 0, if I wrote it down correctly, 1, 1, 0, 1. So what this does, if we look at this model, we have xk plus 1 is 1, 1, 0, 1. So x is a two-dimensional state, xk, and yk is just 1, 0, xk. And I have obviously in my initial value problem some x0. So in this case, this here means that I observe, this is my index k, this is my y. I observe my first state, and this is my slope, like my how does the line go up, and this is my offset. So basically, this one with a given x0, let's say slope 1 and y is. So we have this. We have this line here. So you can also go back in time, then we have this one. So x0 encodes the slope. So this one, T2 would be like this slope. Here it's reproduced at every step. So you have the point where you are plus the slope.
So there's some kind of velocity in some sense.
Yes, exactly. So,
So we're able to model inertia of a system.
we're able to.
Momentum.
Yes, just to have a straight line actually. So what you have is your next point, k plus 1, is where you are right now, plus your slope.
Mm-hmm.
Obviously you can have here some delta H. Is that okay? So x0 encodes both. If we say we start at 5, we are here and have such slope. So x0, this vector here, encodes the position and also my slope. But now if we fit the model locally, so we have local estimates of my x, which do not follow necessarily this equation. We have local estimates, we can have a spline interpolation with a line. So at each point we have some observations, and we can make some depending on how localized I am, we can do some spline interpolation.
So it means that matrix A and C depend on K, on moment of time?
No, A and C are fixed, but basically we get, because they just say what happens here. Here just A and C means that we're having a slope in this case. But what you do is you get different estimates for xk heads, xk plus 1 head, but xk plus 1 head is not A times xk head. Not necessarily. And yeah, if I chose another matrix, for instance, cosine theta minus sine theta, sine theta, and cos theta, this matrix, and my C is just 1, 0. This is a rotation matrix. Determinant is 1, so you have some state here, and with each multiplication you just turn it around. And if you look, for instance, at a projection, what you get is an oscillation, and if we put a factor here, we have an exponentially decaying oscillation. So we can model straight lines, exponentially decaying oscillations, but the main point will be now this localization. So we will introduce the concept of local likelihoods. So, as I said, like the state, it contains the slope, for instance, in this line fitting model, or it contains in this oscillation, it contains the phase and the amplitude of my oscillation. And here, what we do is, when we have observations, and we have our state space model, our autonomous model, we can write down such a likelihood function. And we do the arc max, so we maximize over the likelihood function, which corresponds to a means least square estimation of my states. So x hat n is the arc max over this one. So what is this likelihood function? Well, this likelihood function is assuming this Gaussian setting is just the product over all Gaussian terms. Maybe it's easier to view it as a least squares. So here is the least squares. Here's the errors. Yk is my observation, and y tilde k, well, it might be a bit confusing, but y tilde k is actually this one, so here should be a tilde. So this is the least squares error, and the main point is usually squares, you just sum up all errors equally. But we introduce a localization. How? Localization is in this sigma. It has an index k, and this index k is here. So we have sigma k, which is sigma times this gamma. And I think I need again the whiteboard to illustrate that concept. What we have is actually, in a non-probabilistic setting, we have xn is equal to the arc min, in this case, overall xn of the sum of my observation yk from k to 1 to capital N, and this is very big, so n is much bigger than small n, from y tilde k of xn squared. So this is my observation, and this is my modeled output.
But probably divided by sigma k squared.
For the moment, yeah, just like not yet, but this one would weight all inputs equally,
Right.
and this one is basically xn. My y depends on xn because when I fix sure, from laptop, when I fix one of the states, deterministically all the others have to be the same. So exactly now what you do is you, in a normal transformation from least squares to maximum likelihood, just introduce some variance. But in this case, we want to localize. That means we put a k here. And what does it mean? That we have a weighted least squares. Weighted with a weighted least squares, where here, for instance, my index n, and the weight goes to this one. And this is described by this here. So we have a gamma between 0 and 1. And here is, I just write it, gamma minus n minus k. So when we're at n, the gamma is to the power of 0, so it's unweighted. Then we have, when we're one step left or right, it's gamma to the power of 1, to the power of 2, to the power of 3. And since it's smaller than 1, it's the weighting, the errors don't count as much anymore. So what we want is that our model fits very well here, but the further we go away, the less we care about the errors. And we put this into the sigma because we say that, well, what we have is actually kind of, it's called heteroscedasticity, that our variance increases of our observations. So we pretend that our observations become more noisy. That's why we fit our model better to this case. So the further away we go,
Our local model has less impact since we're moving further and further away.
yes, so on both sides, we can either say that we make, like we want to fit it locally very well, we can say that our variance increases the further away we go from our point where we center about. Exactly. Last 10 minutes, you're almost done. I know it's last day of the year. So in this case, I wrote down the likelihood, but this new concept, which my professor introduced, is this local likelihood. Because in this case, this works well for like for local model estimation. So in this case, before, as I said, when we estimate different x, to estimate different slopes, and we can get a spline interpolation. And how localized it is, we decide on this one. So if we're close to 1, it's not very localized. If it's exactly 1, it's not localized at all. And here, obviously, the closer we go to 0, the more localized we become. And so this is a kind of a new construction, like this local likelihood. So it's still a likelihood, but it has kind of this check symbol here. What changes is, okay, these squares part stays the same, but here we move basically the potence on top of here. What happens is that the power of gamma to this one, what happens is that with this local likelihood, we get the same estimate, because this is just proportional. When we estimate our state, x, in the arc maps, we do not care about this factor in front, so definitely the state estimation will be the same. But now with this new so-called local likelihood function, we are able to get a local estimate of the noise variance. And because what happens in the normal case, due to this 1 over sigma factor, estimating the noise variance would just give absurd results. It would just go to infinity. So our estimate of the noise would be infinity, but with this new function, so if we let in the original local likelihood in an original likelihood function, if we let the index n go to infinity, due to this factor here, we just multiply, 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 and we get, it goes to 0. But on the other hand, this local likelihood function, this one will be still localized, because if this goes to 0, this one will be pushed to 1. So we stay localized. And in this case, we can estimate the noise variance. So the noise variance is just, we take the maximum of this function with respect to the state, to the local state at point n, this is also n, and then we take the argmax, the variance maximizing the local likelihood function. And yeah, so the local likelihood function, in contrast to this other likelihood function for infinite, so in the asymptotics, the local likelihood function is still finite and non-zero, so sigma is also localized and not only the state. And yes, obviously, again, this is connected to vector graphs. How well the likelihood can be computed, again, in a sum product message passing setting, namely the forward message can be computed in this way, the backward message this way. And so if we get the likelihoods by sum product message passing, and here we get the marginal on xn. And so for fixed observations, we can compute that likelihood again in this linear way instead of summing over all random variables. So yes, that would bring me to the end. I just skipped the other slides where we have a Bayesian network. And we get to the summary. So what did we take a look at today? Well, I showed you different graphical models, which are heavily used in statistics and other areas. We have Bayesian networks, the Markov random fields, and vector graphs. And they all, I don't want to discern between them, they all give us very strong tools to develop algorithms. I showed you like the sum product message passing, belief propagation can be used for instance as a Kalman filter, to see the Kalman filter as a sum product message passing. And also, like when we state our inference problem with graphical models, we really can see the structure, and this really helps in solving problems, basically. So, yeah, that's about it. These are, again, the recapitulation, the Fournier-style vector graph, the original vector graph, Bayes network, and this Markov random fields. So yeah, that's it. So I'm very happy to take questions now, and yeah.